Hello, my name is Turab. This presentation is for the paper titled ARCA23K, an audio dataset for investigating open-set label noise. This work was co-authored with Yin Cao, Andrew Bailey, Mark Plumbley, and Wenwu Wang. So, to give some background, you can find large amounts of annotated audio data on the web, for example on audio sharing platforms such as Freesound. These audio clips can be retrieved and labeled using automated procedures, but doing so introduces labeling errors. To remove those labeling errors, you would have to manually verify the labels, but doing so can be costly. For this reason, there has been interest in training audio classifiers despite the presence of label noise. In terms of doing research in this area, there are broadly two ways to conduct experiments. One way is to synthesize the label noise based on a model, while the other way is to use a real-world dataset that contains label noise. The benefit of synthetic label noise is that you can easily run controlled experiments. All of the parameters that characterize the label noise can easily be controlled. This isn't so easy with datasets containing real-world label noise. For example, with existing audio datasets, you can't control the noise rate, which is the percentage of incorrectly labeled audio clips. Being able to control the noise rate would be very useful. On the other hand, synthetic label noise may not accurately represent real-world label noise. In the case of audio data retrieved from the web, there's a good chance that some of the audio clips are out of vocabulary. This means they do not belong to any of the classes we're interested in. Synthetic models typically don't account for this. To close the gap, we introduce ARCA23K, a sound event dataset comprised of audio clips sourced from Freesound. The dataset contains over 23,000 audio clips, and each clip belongs to one of 70 classes taken from the audio set ontology. The audio clips were retrieved and labeled using an entirely automated process, and for this reason a significant amount of label noise is present in the dataset. A unique property of ARCA23K is that you can control the noise rate. To do this, we introduce a companion dataset called ARCA23K FSD, which only contains manually verified labels. This dataset mirrors ARCA23K in that it contains the same number of clips and the same label set. Starting with ARCA23K FSD, we can introduce label noise into the dataset by substituting some of the clips with clips from ARCA23K. The resulting dataset's noise rate is then a fraction of the noise rate of ARCA23K. Using this process, we can effectively control the noise rate of the dataset. To encourage others to extend our work or to adapt it for their own needs, the software used to create the datasets is available as open source code. We now describe how the datasets were created. To create ARCA23K FSD, we used clips from the FSD50K dataset. FSD50K is a multi-label dataset containing over 50,000 audio clips. Our dataset is basically a single label version of FSD50K. To create the dataset, we had to remove several clips that were incompatible. The process resulted in just over 25,000 clips being retained across 77 classes. To create ARCA23K, we first retrieved clips from Freesound using a keyword-based retrieval algorithm. To do this, a query was constructed for each audio set label. For each query and for each Freesound clip, the retrieval algorithm was used to compute relevance scores. Using the relevance score, we can determine which clips are relevant for a given query. For a given clip, the predicted label is given by the query with the highest relevance score. Using the retrieval algorithm, almost 170,000 audio clips were retrieved. This number was then reduced to match the ARCA23K FSD dataset. The classes that lacked enough clips to match ARCA23K FSD were discarded. This resulted in 7 classes being discarded, leaving 70 classes in total. The remaining clips were then used to form the training set of ARCA23K. ARCA23K also includes a validation set and test set. To create these, we simply use the same clips from ARCA23K FSD. To evaluate the retrieval algorithm, the algorithm was used to predict labels for the ARCA23K FSD clips. These predicted clips were then compared to the ground truth labels. Our algorithm considered 84.1% of the clips as relevant and achieved a labeling accuracy around 90%. But bear in mind this does not give us the overall labeling accuracy, since we only evaluated the FSD clips. To measure the overall labeling accuracy and to characterize the label noise, we carried out a listening test. 3 listeners listened to a different sample of 100 audio clips each, and were told to categorize them. Based on these tests, the noise rate was found to be 46.4%. Of the clips that were incorrectly labeled, 75.9% were found to be out of vocabulary. When we looked at the cause for the labeling errors, many were found to be due to the retrieval algorithm. Some were simple mistakes, while others required understanding the context of the metadata, which a keyword-based retrieval algorithm is unable to do. In some cases, the annotations were misleading or incorrect. We also found that many of the out-of-vocabulary clips were quite similar in sound to the in-vocabulary classes. Moving on, we now carry out some experiments to examine the impact of label noise. To do this, we train an 11-layer convolutional neural network. The model is trained on ARCA23K, ARCA23K FSD, and ARCA23K FSD with various types of synthetic label noise, namely uniform label noise and class conditional label noise. We use the mean average precision to measure the performance of the classifier. The results of the experiments can be seen in this graph. As you can see, using the ARCA23K dataset resulted in a reduction in performance of around 14%. This demonstrates that label noise can have a significant effect on learning. On the other hand, it's not as detrimental as synthetic label noise, which reduced the performance by around 30%. In the next set of experiments, we vary the noise rate from 0 to 0.45. Looking at the results, the performance decreases linearly for synthetic label noise as the noise rate increases. In contrast, the plot for ARCA23K is quite different. The performance is relatively the same for lower noise rates, after which it decreases quite rapidly. This again shows that real-world label noise can be quite different from synthetic label noise. To conclude, we introduced the ARCA23K audio dataset to investigate real-world label noise found in web data. The dataset was created in such a way so as to facilitate controlled experiments, namely by allowing the noise rate to be controlled. By carrying out listening tests, we were able to characterize the label noise present in the dataset, and found that most of the incorrectly labeled clips were out of vocabulary. This is something synthetic label noise models typically don't account for. When training an audio classifier, we found that the label noise present in ARCA23K had a significant effect on performance. However, the effects were less detrimental compared to the effects of synthetic label noise. This shows the importance of studying real-world label noise directly.